I leave? Oh. All right, good morning, everybody. I'm going to start this morning by muting everybody because it seems like my sound works a little bit better when I have you all muted. But if you have a question, feel free to unmute yourself and ask that question, or you can always put it in the chat window. I'm going to use the chat window for a moment to post a couple of announcements I'm going to make. So let me find the chat. Okay, let's see. Did not pop up. Come on, try again. Oh, there we go. Good morning, Olivia. Okay, let's try chat one more time. There we go. Okay, so first thing is you have homework 11 is posted, and that is going to be due on Friday of this week. So that's the 27th. The second thing is that we're going to have quiz 4 also on Friday. And the way that's going to work is that I will make it available from 10 a.m., so right after our class, until midnight. And you just need to take it in that time frame. So unless you get extended conditions, you're going to get 30 minutes to do that. You are welcome to use notes and books and things, but you'll have that limit, so you need to know what you're talking about. It's going to cover colligative properties. Mostly I'm going to have questions that are either calculate freezing point depression or boiling point elevation, and give you examples of solutions and say, you know, which has a higher vapor pressure, which has a lower freezing point, that kind of thing. So colligative properties and sections 1 through 3 of chapter 16. Now, chapters 14 and 15 aren't in our syllabus. Chapter 14 is something that's covered in descriptive inorganic chemistry, and so it talks more specifically about some periodic properties and trends of groups. And chapter 15 is on organic chemistry. If you're in my lab section, there is one section of that kind of covers all the different functional groups. And it would be good to take a look at that and just get yourself familiar with what do those functional groups look like? How do I recognize an alcohol? How do I recognize a ketone? That kind of thing. All right, for those of you that just entered, if you look in the chat window, I've posted some announcements. Does anyone have questions about the quiz or about the homework assignment or the previous homework assignment? If so, feel free to unmute yourself and go ahead and ask. All right, well, I'm going to start with just doing a review problem of the colligative properties, and we didn't get a chance yet to talk about the osmotic pressure. So I'm going to talk about that for just just a minute or so, and then we'll go back to chapter 16. Let me find, there it is. All right. This should be posted on the chapter 13 page. Everything else will be posted on the chapter 16 page. Okay, so let me, this. You're gonna pop up here. I can see me and I see a blank screen. It's not happy with that. Let's try that again. I'm getting a little pinwheel with my arrow here, so I'm gonna have to wait for that. So just as a reminder, our colligative properties include the vapor pressure, and that will go down. Our freezing point will also go down with higher concentrations, and our, oops, it stopped sharing. Okay, let me try this again. Oh, okay. I'm gonna have to manage my PowerPoint for a second. So our freezing point will go down, our boiling point will go up. It's called boiling point elevation. And our osmotic pressure, which we haven't talked about just yet, that is also going to go up. So those are the things that we need to be paying attention to. So while I'm waiting for my PowerPoint to restart again, I'm going to talk a little bit about osmotic pressure. So you probably are familiar with the term osmosis, usually used in biology, and talking about water being able to go through a semi-permeable membrane, which usually means a cell membrane. And we don't allow a lot of other things to go through that membrane quite as easily. And so what happens with osmotic pressure is that you have solutions on either side of this membrane, and one of them is more concentrated than the other. So the example we're going to look at is where we have an extreme case where we have pure water, and then we also have something that has a more elevated concentration. Okay, my PowerPoint is back up, so let me try sharing this again. Oh, it's still on share. Okay. Let me go back and do this. PowerPoint, share. Okay, so these are the four colligative properties here: vapor pressure, freezing point, boiling point, and osmotic pressure. So it's important to know what direction they're going to go. And then it's also important to know, what is meant by each of these. Okay, so osmotic pressure. Let's say this line in the middle of here is a semi-permeable membrane, and this is just like an aquarium tank with water. And on one side we have pure water, and on the other side we have salt water. So osmosis would be that the water could go back and forth, but the salt couldn't. And so what's going to tend to happen is that because there is salt and water over here, the molecules at the surface of this membrane are not entirely water on this side, but on the other side they're all water. And so we're going to have a net flow of water to the saltwater side. We'll get a little bit of water going back in the other direction, but most of it is going to be on going to the saltwater side. And so as a result, the water level will increase on the saltwater side, which I guess in this particular tank is going to cause it to spill, but it's going to decrease on the pure water side. So we have a net flow in that direction, but a little bit of flow going back in the other direction. Okay, so the picture from, let's get some definitions here. So a semi-permeable membrane is a barrier that allows the solvent molecules to pass through, but not the solute molecules. And again, this PowerPoint is posted elsewhere, but if you like to have these in your notes, writing it down is definitely a good way to help commit it to memory. So the more ways you process information, the better you're going to remember it. So writing it down, even though it's available in another form, is not a bad idea. So what's going to happen is that the solvent will pass through in both directions, like we showed on that example there, but more of the solvent, and in most cases we're talking water as our solvent, are going to flow into the solution rather than back into the pure solvent. Or if we just have different concentrations, more is going to go towards the higher concentration than the lower concentration. And the net effect of this is that we're going to be bringing those concentrations closer together. So here we have what's called a U tube. Doesn't show us any videos, but it's shaped like a U. And so on one side we have our pure solvent, the other side we have a solution, and we have water flowing from one direction to another. And so if we're looking at this at a molecular level, you can see at the bottom on the left-hand side, there are only these blue water molecules. On the right-hand side, we have both the blue and the green. And the green are just too big to get through that membrane, and so there's a net transfer of the water going into the solution. Okay, so this blue thing is our semi-permeable membrane, and there's a net movement of the solvent. And let me know if you need me to slow down or go back. You can just turn on your microphone and say, hey, I wasn't done with that slide, and I can go back for it. All right, so this is that same definition if you were still writing it down. So the barrier that's allowing the molecules through. And our first step is going to be to allow that solvent to pass in both directions, but more going into the pure solvent. The next thing is that because we're putting solvent into the solution, that solution is going to become more dilute. So remember, our concentration is always going to be either the solute divided by everything or the solute divided by just the solvent, but increasing the solvent is going to increase the denominator. So when we increase the denominator, the whole concentration is going to decrease. So it becomes more dilute. So here we have a second picture. As we dilute this side, we're also increasing the amount of our solution over here because we've added water to it. And so there's going to be a difference in height. Now, you remember from when we did our unit on gas laws last fall that when we have gases, we can measure those gases with a barometer or a manometer, and they often will use mercury in a tube, and the difference in the height of the mercury is going to show us what that pressure is. So we can use the similar idea here. This height here represents the osmotic pressure. So if I had my setup like this height would be a measure of my osmotic pressure. Okay, so as the solution volume increases, and that's where it's becoming more dilute, we're going to be increasing the pressure. The solvent volume, so the pure solvent, is going to decrease, and so we decrease the pressure on that side. And the difference between those two is our osmotic pressure. So the pressure differential shows the rate at which the solvent moves into the solution. So the long and the short of that is really just to say that when we have a higher concentration, we're going to get a bigger pressure differential. So we just need to know that the more concentrated our solution is, the greater the osmotic pressure would be. So what we could do is use some kind of a piston to push down on the side where the solution is until they're the same level, and the pressure that we'd have to push down on that side is equal to the osmotic pressure. So why would we want to do this? Well, let's say you're going camping, or let's say the apocalypse happens and all freshwater supplies, tap water runs out. So you go down to Elkhorn Creek or whatever creek is near you, and you grab up some water and you're like, oh, this is kind of nasty. Well, you can use what's called an REOS, so reverse osmotic pressure. And what you'll do is you will push that water through a semi-permeable membrane. So you push it in on this green side, and then only the pure water would come out on the other side, and you'd be able to have pure drinking water. So it does have a useful application. All right, so before I go on, Does anybody have any questions? All right, so I'm going to move on to doing our example of a boiling point elevation this time. So I want to remind you that while a lot of our examples involve water, they don't always. Oh, looks like I got an attendee here, I think. Oh, no, something in chat. So let's see. Can I go back 2 slides? Yes, I can. All right, so the person who just typed that, is this the slide you want, or do you want the one before it? One more. Okay, that's what I thought. Oops. There we go. Okay, so while we're getting notes taken on that, when you have something other than water, when you calculate your final boiling point or when you calculate your final freezing point, it's not going to be just a matter of looking at what the change is. So we know that since water freezes at 0 degrees Celsius, whatever the change is, that's what the temperature is going to be, because it's a negative change, so we'll end up at negative whatever. But if we're not using water as our solvent, then we have to pay attention to whatever the freezing point or boiling point of that substance is. So my example that I'm going to be using here is going to be, I think, chloroform, and chloroform has a different boiling point. So we're going to look at how to do that calculations. It's the same calculation, we just need to pay attention to what the boiling point is. All right, so before I move on here, am I good to choose or move to the next slide, Clay? All right, thank you. Okay, so if we look at chloroform on this chart here, we're going to be paying attention to its boiling point is 61.7 and its KB is 3.63. So that's how much it changes per molal when we have a solute involved. Now, chloroform is polar, but it doesn't have hydrogen bonding the way that water does. So we're going to have some differences in things that could be dissolved there. So I think I just chose a generic solute. I didn't identify it. All right, so the normal boiling point of chloroform is 61.7 degrees Celsius, and its KB is 3.63. And the question we're going to answer is, what concentration of solute is required to raise the boiling point to 65 degrees Celsius? So we're only going from 61.7 to 65. We're not going to raise it an entire 65. So our delta T is not 65. We're going from 61.7 to 65. So that seems to be a mistake that I saw people making on the last test when they were doing delta T, is that they were trying to use the whole range or going from 0. We have to look at where's our starting point, where's our ending point. So 65 is the ending point, 61.7 is the starting point. We have our formula here. Chloroform is entirely a covalent compound, so I, our Van 't Hoff factor, is going to be 1. It doesn't break into ions. And then our change in temperature is going to be 65 minus 61.7, or 3.3 degrees Celsius. So what we'll need to do, and I need to move this so I can see again. Come on, move out of my way. There we go. We'll plug in those numbers. So the 3.3 is the delta T, 1 is I, KB is 3.63, and that has units of degrees Celsius per molal. And then we're solving for M. So notice in this case that lowercase m within the second set of parentheses is serving as the units, but in the third set of parentheses is the marker for our unknown. So we're saying our unknown is the M. So that lowercase m can be used in 2 different ways. And I know that that can be confusing, but you'll see it that way on tests. So I want to make sure you see it that way here as well. So if I solve for m, then my concentration is 0.91 moles per kilogram. So I have that answer. I want to make sure I'm answering the question before I move on and go on to the rest of my test or whatever. I'm going to go back up here, and it asks, what is the concentration? So did I find a concentration? Yes, molality is a concentration. So I'm going to give you a second to process that before I move on. All right, so now I'm going to, oops, gotta get out of there. Now I'm going to pull up the PowerPoint we were looking at the other day on kinetics. Before we jump into that one, are there questions about the colligative properties or what you might see on the test or quiz? I am likely to move the exam 2 date or exam 3 date. I thought we would be done by the end of March with chapter 16. It looks like we're going to go a little bit into April, so I'll let you know the date on Friday. Okay, so let's see. I'm going to dismiss that, and I'm going to go back to sharing my PowerPoint. All right, so we talked about with kinetics, there being various things that can affect the rate of a reaction. I saw several of you were doing the vocab. The rest of you, don't forget that you need to do those definitions. Just get yourself familiar with the terminology that we're using in kinetics so that as you're hearing it in these lectures, you're not getting lost. Okay, so we're talking about collision frequency, because molecules have to collide in order to react. Anything that is going to increase that collision frequency is also going to increase the reaction rate. So if I have a higher temperature, that's going to increase the reaction rate. Let me pull this up here. If I have higher concentrations, just like if there's more people on a dance floor, it's harder not to run into people than if there are very few people on a dance floor. So higher concentrations are going to mean more collisions. And those are the two main factors that we look at. But we're also going to see that if we have things in the same phase, like they're both gases or they're both liquids, they tend to react better. Or if we involve solids, the more surface area we have is going to make a difference. All right, so we said we are measuring, oops, the change in the concentration of the product over the change in time, or the negative of the concentration of the reactant over the change in time. And the reason we use the negative for the reactant is since it is going down, that negative cancels out the negative that we would get from final minus initial. So the rate is always written as positive. We just put the negative in front of the formula to make it positive. And we looked at a graph here illustrating how the reactant is going down and the product is increasing. Notice it's not in a straight line. And this is because as we decrease our reactant, then we're decreasing the concentration. And we said concentration was connected to the ability to react. So as we decrease the concentration, the reaction slows down. And so we lose a little bit less for every 10 seconds, 30 seconds, minute, second, whatever unit we're using. All right, so here's a collection of data that we might have. This is the same reaction. So we have the ethene here and we have the oxygen here. But in this case, instead of measuring the ethene, we're measuring the ozone. So it says concentration of ozone. So if we wanted to know the rate at any section of time, we would use this formula, the negative of the change in concentration over the change in time. So let's take a look at what that looks like. This is the same data that's written here on the right-hand side. If we want to know the rate of the reaction, we might say, okay, well, what's the rate of the reaction overall for the whole time that we're looking at? In which case, we would say, let's take the change in the concentration. So we'll take our final 1.10 times 10 to the negative fifth minus 3.20 times 10 to the negative fifth, and we would divide that by 60 seconds because that's the total amount of time that has passed. And that would give us this amount here. So we have a concentration change, and then it is in units of concentration, in this case molarity, and in this chapter we'll mostly use molarity per second. Hang on just a second. Well, you'll have to listen to my phone ringing in the background. I'll let it go to voicemail. Okay, so that concentration represents the slope of our curve. And so since we have a curved line, the slope isn't constant. So if we look at the slope at different places, it's going to be different things. So what I'm going to look at next is, what about in the first 10 seconds? So if I'm looking at the first 10 seconds, I'm going to do my final minus initial is the 2.42 minus 3.20, and my total time elapsed is 10 seconds. And that's going to give me 7.8. So I'm going to see that there's a much faster, more than twice as fast rate change at the beginning than there is overall. And then I could also look in the last 10 seconds doing the subtraction of these last two numbers. But again, 60 minus 50, it's still only 10 seconds that have passed. So I'm going to divide by 10 seconds, and it's going to be much smaller. So you can see that depending on whether I'm looking at the first 10 seconds, the last 10 seconds, or overall, I'm getting very different numbers. Now, the overall is the same. So I have, I'm sorry, the overall order of magnitude is 10 to the minus 7 for each of these. So it's 3.5, 7.8, 1.3 times 10 to the negative 7 each time. So that on the grand scheme of things, the rate is similar, but I still have differences in how much that rate is. Okay, so here's a graph that kind of shows those different things. B is the first thing that we did. This is the average over the entire 60 seconds. And this is still that same chemical equation, the ethene reacting with ozone. So we're looking at the ozone concentration on this graph. B is showing us the average. And so it's not really lined up very well with the red, and the red is our overall curve. So we're seeing the concentration of ozone decreasing across the red. And what we're trying to do with each of these calculations is approximate the slope. So you can see that B doesn't really approximate any part of the slope that we were looking at. C here approximates that first 10 seconds pretty well. You know, we get pretty close there. And E, the last 10 seconds pretty well. So the smaller the window we have, the smaller or the closer we are to interpreting that slope. So some of you have had calculus before, some of you haven't. That's okay. But one of the things that calculus does is says, well, what happens if we can narrow that range that we're looking at? Can we estimate that slope better? So what I want to do is find A. I'm interested in this initial rate, because the initial rate is where I know that concentration best of all. I know what I put in the test tube or the beaker or whatever. And if I can figure out that initial rate, then I can figure out some other things about my calculation. I might also want to know what it is further down. And the way that we do this is by finding the tangent line to the curve. Okay, so C is a decent approximation of the initial rate. It's a lot better than B is, but it's still not great. And so what we're going to do later on in the chapter is we're going to use what are called integrated rate laws. So when you hear integrated, you should be thinking, oh, that has something to do with calculus. You don't have to do the calculus. I will do the calculus and just give you the end result, the end formula that you can plug things into. But what we're going to use now is A, is the initial rate there to try and understand the order of the reaction. Okay. So the things we looked at here were the average rate. So that's over any given time, and that's where we have the concentrations at those 2 points and how much time has passed. So over a period of time, how quickly does that concentration change? The instantaneous rate is at a particular instant. And so we find that by the slope of the line tangent to the curve, just touching the curve at one point. In order to do that effectively, we really have to use calculus. And as I said, you're not going to have to do the calculus. I'll show you how to get that point. The initial rate is an instantaneous rate at the moment the reactants are mixed. So I'm going to give you guys about, let's say 45 seconds if you're typing things down here or writing things in a notebook. In the meantime, feel free to ask any questions. All right, so let's move on here. This is a calculation that I don't generally ask very often, but it does show up on standardized exams. So if you are asked to find the rate with respect to one chemical versus the rate with respect to another chemical, this is what you would use. So I'm briefly going to talk about it. I'll come back to it again on Friday. I'm not going to go into a lot of detail on it, and I won't ask you about it on your test. But let's say that we know the rate with respect to A, and A was maybe our ozone. But we wanted to know how quickly the ethene was changing. So we can use the formula to show us how, the chemical equation to show us how that rate is changing. So if we have a coefficient of 1 for A and a coefficient of 2 for B, then that means every time A changes by 1, B is going to change by 2. And so its rate is going to look a little bit different. And so the way that we would compare those is if I'm trying to go to B, I'm trying to get to delta B over delta T, I'm going to need to take those first two parts of the equation that involve A and B, and I'm going to move the B, the lowercase b that is the coefficient, over to the A side. So what I'm going to have is lowercase b over lowercase a times the rate with respect to A. So this is very similar to how we've done unit analysis in the past. We're going to multiply by what we want. We're going to take the coefficient of B, because that's where we're trying to get to. So we're going to multiply by that coefficient, and we're going to divide by the coefficient of what we know. We know the rate with respect to A. So that's how we can find those rates. All right, I think, let's see. Oh, no, I do have a little bit more here. Okay. Rate laws. Okay, so we've talked about finding what the rate is, and that's not considered a rate law. What that's considered is just what the rate is, calculating a number. It's not an expression. It's not something you can plug things into. It's just, this is what the rate is. Ooh, I've got a question. What factors would increase the rate of the reaction for a solvent moving into a solution? Okay. I'm not sure what you mean by the solvent moving into a solution. So usually when we do a rate, we have things that are mixed together and we're just looking at them already mixed together, so we don't increase that. I think what you might be doing is mixing up the osmotic pressure, which has to do with colligative properties, with the rate here. So with osmotic pressure, we're not really talking about rate. With this, we've talking about things that are already mixed together. So can you clarify your question? And Elizabeth has noticed the meeting time is running out. So I'm going to give Clay a chance to finish typing what he's typing. And in just a minute, we are going to end the meeting, but then we're going to take maybe a 2-minute break, and then we'll start the second session. So you should have had in your email, or if you accepted the meeting, it went to your Outlook, a second part 2 that you can click on, and you can go to that. All right. So I'm going to go ahead and end the meeting here. We will come back in 2 minutes.